We can clap. The import from Keynote to PowerPoint is dreadful, so the audio video here is going to be lacking some. But welcome to my talk about the future of the brain. I wanted to start with a presidential proclamation. Over the years, our understanding of the brain, how it works, what goes wrong when it's injured or diseased, has increased dramatically. However, we still have much more to learn. The need for continued study of the brain is compelling. Millions of Americans are affected each year by disorders of the brain. Today, these individuals and their families are justifiably hopeful. Does this sound like a talk that Barack Obama might have given on the Brain Initiative to anybody? It should, but it ain't. It's not that. It's from 1990, the quote that I just read. And so, to some extent, it's a lesson in humility that for 25 years, people have been saying, we're just around the corner. We're going to understand neuroscience tomorrow. And the truth is, 25 years later, not that much has changed since 1990. We still know remarkably little about how the brain works. My one-liner on the future of the brain is, if we can understand how the brain works, then our possibilities are limitless, but we don't yet understand it. So 25 years later, we can't reliably use brain scans to diagnose mental disorders. You may know that the new DSM manual doesn't make any reference to anything in the brain, which is sort of remarkable since all mental disorders stem from the brain, but it's a fact. There's still no cure for autism, for Down syndrome, schizophrenia, and so forth. The DSM doesn't, as I said, list any brain markers for mental illness, etc. And lots of fundamental things remain unknown. Like if you take any introduction to psychology class, you will know that we have short-term memory, but we still don't know the biological basis of short-term memory. It's like a foundational basic fact about the mind that we have it, we don't know how it works. We still don't know what Broca's area is. Everybody thinks it has something to do with language. If you read any textbook, it will say that's the area of the brain responsible for language, but nobody has any idea what Broca's area really does. It's also involved in music and motor control and imitation, all kinds of other things. We still don't know how the brain processes sentences, which is what I study most, I suppose. We still don't know how the brain decides which area to use at any given moment. So the most salient fact from the fMRI literature, where you do brain scans, is that everything that you do invokes a sort of different constellation of brain areas right there immediately on the fly. So if I made up a new task for you, I said, hold two microphones. Now turn them upside down and up. That's a little bit risky with the feedback. You could do that. Your brain would figure out on the fly how to do it immediately. How does the brain do that? Nobody knows. Nobody knows what the cerebellum is. Nobody knows how information is encoded in long-term memory. All these most basic things. Is the brain digital or analog? Ask 100 neuroscientists and you'll get at least 50 different answers and no consensus on any of these things. Neuroscience has been around for 150 years, but we still don't have a theory of how the brain works. So I have on the left a figure of people's understanding of chemistry before they figured out the periodic table. That's basically where we are in neuroscience. We're long before a periodic table, before any systematic understanding of what it is the brain does. This has caused some people to give up altogether. You probably know David Brooks, who writes for the New York Times. He had a piece a year and a half ago called Beyond the Brain, where he just sort of threw up his hands and said, you know, all this brain imaging stuff hasn't told us anything. Maybe, you know, the brain doesn't really matter after all, which is a ridiculous claim, but, you know, he's got a column in the New York Times, so he can write what he wants. I have a little bit of space in the New Yorker, and I wrote a kind of reply called The Problem with Neuroscience Backlash, and you can go read it later if you want. I sort of picked apart his arguments one by one. His biggest argument was basically that there's no single location for any particular thing. But that doesn't mean that the brain doesn't do something. It just means that the brain uses what we call distributed representations. That things are spread across the brain in order to solve them. It'd be like saying, I listened to I don't know, Help by the Beatles, and there's no one musician making the music, so it must not be made by musicians. It's an absurd argument. Of course, you know, any song that's not an a cappella song is going to be distributed across multiple musicians. Anything in the brain is distributed across many different processes. And I'm actually pretty optimistic about neuroscience maybe getting somewhere in the next few decades. Another piece in the New Yorker I wrote was called A Laser Light Show in the Brain, which was about optogenetics. How many people here have heard of optogenetics? Optogenetics is the coolest thing to hit neuroscience in at least 50 years. And what it is a way of controlling individual neurons in the brain. There's some limitations on it. It's not perfect. But most of the problem with neuroscience has been that what we've been doing is looking at correlations rather than causation. So you have somebody do something, you see what things light up in the brain, and you make guesses about what's going on. But this new technique, optogenetics, allows you to use a laser light to illuminate a neuron and make it fire. So you can actually causally control the system. This is a big deal. It was invented or discovered, I guess invented is the right word, in 2005. It's basically synthetic biology doing some re-engineering of genes. And everybody uses it now. Thousands of labs use it. It's a major new technique that's going to have a big impact. I couldn't get, for technical reasons, this video to play. But what we have on the right are some videos you can go home and look on YouTube where people can look at 80% of the neurons in a larval zebrafish's brain, growing zebrafish, 80% of the neurons all at one time. So part of the problem is we haven't been able to look at the individual neuron level. A voxel in an fMRI brain image is 70,000 neurons. We can't dig down to the individual neuron level. We have new techniques like calcium sheet imaging that are completely changing the level of resolution at which we can study the brain. So there is some reason for optimism, but there's also some reason for concern. I want to talk today partly about why I think neuroscience is stuck on theoretical terms. So we're starting to get at a position where we're going to have more data than anybody's ever imagined. We're going to have petabytes of data from the Obama Brain Initiative and other places, or exabytes of data, I don't even know which, probably exabytes or even beyond. So enormous amounts of data where we track lots of individual neurons simultaneously while people are engaged in behavior, at least while laboratory animals are engaged in behavior, but we still don't really know how to analyze that data. And I think that we're a little bit stuck on the theory end. So I said once in the New Yorker, and it pissed a lot of people off, but in the end I think I was right. I said neuroscience has still not had its Newton. So a couple people wrote in and said, well, what about Ramoni Cajal, who is a great neuroscientist? And Cajal figured out that there are neurons and that they're important, but I still don't think he is at the level of the Newton of saying, how does all of this stuff fit together? I think the number one obstacle in neuroscience, and probably in a lot of sciences that aren't physics, is a misguided search for silver bullets. So people are looking for like the one true explanatory principle that will explain them all. In physics, that makes sense. In physics, you might conceivably find a unified field theory that would put everything together. But the brain is the product of biology, and biology is kind of a mess. Kluge, this earlier book, is about how the brain builds, or evolution builds new systems on top of old systems, and newer systems on top of those systems, and so forth. The evolution doesn't have the luxury of taking brains offline while it releases version 2.0 or something like that. So evolution is just accumulating things and sort of more crud on top of more crud. I mean, from an engineering perspective, our brains aren't simple, they aren't elegant, and yet people keep looking over and over for simple and elegant explanations. This goes back to theories like behaviorism. Probably many of you have heard of B.F. Skinner. Certainly if you ever took a psychology class, you would have heard of B.F. Skinner. And Skinner tried to explain the entire function of the mind and the brain. He didn't really like talking about minds in terms of basically a simple principle of reward and reinforcement punishment. And that was basically it. So whatever you did was a function of your reward history. Now we know that there's some truth in that. We are driven by rewards. If I tell you that if you come upstairs, up to the podium, spin around 7 times, and I'll give you $700, probably people, a lot of people will like the $700, and I will manipulate your behavior by offering a reward. But that doesn't mean that defines all of what you do as a human being. As Chomsky famously argued, it doesn't really tell us anything about how a child learns language. So it was a simple theory that captured a tiny aspect of how the mind works, but only, I think, a tiny aspect. Then, I don't know how many people know the field of neural networks. It's become very popular lately. It was popular in the 1980s. It sort of comes in ebbs and flows. How many people know the term deep learning? It's very trendy in AI. Deep learning basically starts with this field of parallel distributed processing, or at least that's the kind of second era. There was an era of it in the 1950s, it died out, then it resurged in the 80s, died out, and it's come back with a vengeance. But nobody has ever figured out how to actually explain the complexities of the brain. It's much better than before, so deep learning is now able to do a lot of speech recognition. So when you use Siri and it recognizes the syllables that you use, Siri is using some variation on neural networks, at least in part, to recognize your syllables. On the other hand, when Siri has no idea what you're talking about, even though it's able to decode your individual words, that's because nobody knows how to build a neural network that actually approximates what a human being can do. So I actually had a slide about deep learning. Somehow I combined two things together here. I'll come back to the one on the right. Another trendy thing right now is in Europe, they're trying to emulate the entire brain, to build a simulation that captures neuron in the brain, every synapse in the brain. So we have 86 billion neurons, we have trillions of synapses. And the idea of this project, which is being funded with €1 billion, so it's a very expensive project, is to try to simulate the entire brain. Henry Markram on the left alleged in a famous TED talk that he could build this in 10 years, that by the end of a decade we would build brain simulations where you could simulate drugs in silico rather than in, say, laboratory animals. You could just write a computer simulation. As far as I can tell, nobody in the field thinks that we're actually remotely in a position to do that. It's a nice dream, and I can talk a little bit about the dream, but at the moment we don't even know which things should go into the simulation. And the simulation of a brain is likely to be sensitive to initial conditions in the way that the weather is. So anybody who lives in New York should remember that a few weeks ago we were promised the storm of the century. I changed flights from Austin, Texas to get back here in time so that, you know, because there was going to be 4 feet of snow or whatever, and then we got, what, 6 inches or something like that. And so you might get the same problem in a brain simulation, that because tiny little differences can lead to very different outcomes. You think you have a simulation of an accurate brain, and it turns out to be a simulation, let's say, of a disordered brain, so not what you're after. The core of the problem, I think, is that in neuroscience, people are looking for something that they call a single canonical cortical computation. And what they mean by it is that there would be one principle, one kind of brain circuit. There would be many, many copies through the brain. And the hope is, if we could figure out this one circuit, then we'd be kind of done. And the people who are trying to do this simulation in Europe are basically banking on this. They can't actually measure all of the 86 billion neurons in the human brain, but they're hoping they can kind of statistically approximate it. So they're working right now mostly on a single cortical circuit, a single cortical column. They're hoping if they get that column right, there are many of these columns, they'll be able to infer the rest. It's a very popular idea in neuroscience, and I think it's a bad idea. Like a lot of bad ideas, maybe some good ideas, there's an element of truth. There's a reason why people are looking for this, which is that if you take any part of the cortex, that's the part of your brain that's involved in vision, in language, in motor control, in reasoning, it looks remarkably similar. Many people have read Steven Pinker's How the Mind Works. Is that a book that's familiar to people, or know some evolutionary psychology? The idea in evolutionary psychology is that the brain is kind of like a Swiss Army knife, that there's a bunch of modules in the brain that are devoted to particular individual tasks. Apologize for my cough. And the idea, if the brain has many of these modules doing particular things, you might expect that each part of the brain would look physically different if you just kind of put it under a magnifying glass. And that's not the case. If you look under a magnifying glass or even a decent optical microscope, what you see is a lot of similarity. There's some basic homogeneity of the brain. So you find a 6-layer cortex pretty much from the front of the brain to the back of the brain. Perhaps someone is bringing me water. I have a tiny bit here, but I would love a refresher.
Wine.
Wine? Oh, that's probably not going to. Is this bottle supposed to be for me? There's an unopened bottle of water. Or this. Excellent. One way or another, we will help this problem a little bit. Wine will turn into water, and soon we will have an understanding of the brain. Or the other way around. All right, so there's this 6-layer cortex, which presents a bit of a mystery, because different parts of the brain obviously do different things, and yet superficially they look similar. So some parts of the brain do vision, some parts do language, some parts do decision making. All of those things actually rely on multiple parts. Why does it all look the same? So that's one reason why a lot of people, especially coming from physics, I think maybe we'll find this one magical principle. We have, gravity, we can explain lots of things with that. We need 4 principles, we'll put them all together, and we'll be able to explain all of physics. I mean, this is the dream of physicists, but I think it's dubious in biology. You will hardly be able to read that at all. Probably I will hardly be able to read it at all. This is part of the problem of translating from the Mac to the PC here. But what this slide says is that people have been looking for this canonical cortical circuit for 40 years, at least back to 1979, arguably back to this guy Ramon y Cajal, who was writing around 1910. And then I have a long-winded quote here from Douglas and Martin, who are the people pushing this in the field, saying, well, it's proven elusive, which is to say, we haven't found it yet, despite having looked for this thing for 40 years. And then I have at the bottom my favorite quote that I think applies here, which is actually from Bono, which is, I still haven't found what I'm looking for. So if it's there, people keep trying to find it, but with not a lot of luck. And then there's another reason to really seriously doubt any theory that's trying to capture all of the brain in one magic principle, which is at every level that you look in the brain, actually what you really see is enormous complexity. So on the left is a now out-of-date picture, a diagram, kind of circuit diagram of the visual cortex in a macaque monkey. And it used to be you could not go to a neuroscience talk without people showing it. And nobody really knew what it meant. It sort of looks like spaghetti at some level. But part of what people realize is that there's a lot of complexity in how individual sub-areas of the brain interconnect to one another. And obviously, we're not going to understand how the brain works unless we can read the wiring diagram. There's no reasonable hope of that. I mean, like trying to understand how a radio works without knowing what transistors and resistors are and how they connect to one another and so forth. And it turns out that diagram on the left is actually a wild oversimplification. There's new data that just came out a year ago which shows basically that every area in a macaque brain more or less connects to every other area. And the real thing is that they differ in 5 orders of magnitude by how much they connect to one another. So there are hundreds of areas in the macaque brain, and there's this very detailed wiring diagram that makes it all work. And it's probably unrealistic to expect you're going to get that with one principle, and you're going to kind of derive the rest like a mathematical equation. In the top center, and I'm sorry you can't see it, but it's from a wonderful app called Cognitive Consilience, which you can get for free. Some people have tried to plot everything that we know about the 6-layered cortex. And even though it's not very visible here, you can see there are like hundreds of different connections in this stereotype circuit within the 6-layered cortex. So there's a lot of complexity at that level too. And then on the right, I have something indicating all of the complexity at different synapses. So each synapse, we have trillions of synapses, has its own complement of hundreds of different proteins inside of it. And it's likely that each synapse works differently, or each cluster of hundreds of thousands or billions of synapses, who know, work on its own principles. How many different kinds of neurons are there in the brain? Anybody know? Different kinds of neurons. So like you have white blood cells and red blood cells. That's 2 kinds of cells. How many different kinds of neurons in the brain? Trick question, because nobody knows. It's the number one goal of the Obama Brain Initiative is to answer that question. Guesses are between 500 and 1,000. It depends a little bit on how you count. But something like, ballpark, there's several hundred different kinds of neurons. And nature doesn't usually do things without a reason. They're probably not interchangeable parts. They seem to have different properties. So they're electrically different. They connect in different places. Some of them have spikes that last a long time. Some have spikes that decay more slowly. There's some reason for all of this. So of course, I'm not saying that evolution does anything for a purpose, but anything that doesn't have a purpose tends to disappear. So there are a lot of things, if you don't get them right, you have mental illness or you don't even survive at all. So there's an enormous amount of detail that we're going to have to unravel if we really are to understand the brain. Another problem with this canonical idea is that it misses what I think is the most important idea that has come from evolutionary biology in the last couple of decades. I don't know if anybody would know the term conservation in biology. But what conservation means in biology is that we see the same protein families, same gene families over and over in many different animals. So the genes that are in a fruit fly and the genes in a human being are like 50% similar. And the genes that are in a chimpanzee and a human are 98% similar. So the same toolkits are getting used over and over again. But at the same time, there's something called duplication and divergence. What that means is that in older creatures, you often find one gene. And in more recently evolved creatures, if that's the right way to put it, you will find many copies of a given gene, and they're each different. And so some stay the same way. They fulfill the function that was originally there, and others are free to vary, and that creates complexity and richness. And so the biggest trend in human evolution is we have a lot of this duplication and divergence, especially in our brains, which means we have a richer set of instructions. What are genes? They're sets of instructions for building the brain. So there's some enormous richness in there that is being overlooked in the idea of finding this one canonical circuit. And then the canonical circuit gives you no account of why one of these two creatures can talk, which is what I really care about as a linguist, and the other one doesn't. Like, our genomes are mostly similar. If we're using the same canonical circuitry, why, when you raise, I won't tell you which is which, but if you raise the appropriate one in a human environment, it will learn to talk. Maybe it's a poor example, and the one on the left didn't really learn, but you get the idea. The second problem is what I call the streetlight problem. Do you all know the old joke about the drunk looking for their keys and everybody clusters around? They're all looking in the same place for the lost keys. Nobody's finding it. Somebody finally asks, why are you all looking in the same place? And they say, well, that's where the streetlight is. And of course, the point is maybe the keys aren't under the streetlights. I think that's part of what's going on in neuroscience. Neuroscience has had one really good idea, which I'm going to tell you in a minute. It's been around since the late 1950s. It's very useful. I'm going to tell you in a minute that I don't think it's enough. Not because I think it's wrong. I think it's a true fact about the brain, but it doesn't go far enough. The idea, which some people call the greatest single influence on the ways neuroscientists think about the brain during the second half of the 20th century and really now, is the idea of a hierarchy of features. The idea is that if you have some neurons that do very simple-minded tasks, and you put them together, they're sort of supervisors. You can think of it like a corporate hierarchy or something like that. Their supervisors can do more complicated things, and then more complicated things as you raise up this chain. So you start with simple cells that notice things like a difference between light and dark. You put these together, and then you can notice the difference between a line and not. Then you put those together, and you start to notice, say, intersections between lines, and then you have more abstract ones that recognize letters and words and so forth. So this is the idea of a feature hierarchy. And it's a really important idea. It's clearly part of what goes on in the brain. Hubel and Wiesel won the Nobel Prize for discovering this in the 1950s, 1959 is when they won the prize. There's some pretty sophisticated versions of this. So Christoph Koch, who I'll mention in a few moments, did this work, some of you may have heard of it, where they're discovering individual neurons in human beings. So we don't usually study single neurons in human brains. Why not? Because you have to open the skull in order to get the data. And most of us are not that interested in science that we want to donate our own personal brains to figuring this out. But there are people who have to have surgery for epilepsy where their skull is already open, and during the preparation for surgery you can actually poke individual neurons and measure them and so forth. There's some work going back to the 50s of this sort. So it turns out that you can find individual neurons that respond to very specific things. Like in one of these studies they found an Oprah Winfrey neuron, responded to Oprah Winfrey and nothing else. Another one was a Jennifer Aniston neuron. It responded to Jennifer Aniston. It responded to a picture of her face, to the word, and so forth, and not to anything else. So we can have very specific neurons, and we believe that these are at the top of these hierarchies. So if what we're talking about is categorization, the hierarchical concept seems to work pretty well. We're not sure of it. There's still questions to be filled in, but we have a pretty good handle on how that part of our brains and minds might work. That idea is also the impetus behind a wide range of computational models. If anybody's heard of Jeff Hawkins and his book on intelligence, the model that he has is basically based on this idea. Deep learning, which I have on the right, which is, a bunch of you have heard of, it's been in the front page of the New York Times and covered a lot by Wired and so forth, is really like the theory of the moment, is also based on this idea. So it's a ubiquitous idea. Google had a thing called a cat detector, also on the front page of the New York Times. They fed in about 20 million stills from YouTube videos. The system self-organized, and then they did basically neuroscience on the system, and they discovered that one of the neurons responded to cats, and there's a lot of press about this. That's also built on the same principle. But it turns out that none of these systems are remotely as good as humans. They can be as good as humans at very narrow tasks. There's something called ImageNet, where you have to recognize 1,000 different categories. And the systems are actually pretty good at that. But only if you're looking at, say, photographs. They don't generalize in the way a person does. So a person, once I have a 2.5 or 2 1/3-year-old child, for example, once I show him a picture of a cat, he can recognize a line drawing of a cat or a cartoon of a cat and so forth, not just the individual images that he's memorized. We don't know how to build machines that are flexible in that way. It turns out that they're very easily fooled. So this is a slide from someone else's work that just came out where they took deep learning, this like trendy thing people are spending hundreds of millions of dollars at Google and Facebook and so forth, to hire experts in this technique, you can easily fool it. Like the pattern of yellow and black stripes, you feed it into one of these systems, it's basically a hierarchical feature detector, and it says, oh yeah, I know what that is, it's a school bus. Now, some people would say humans are vulnerable to optical illusions. We all know about the yellow and gold dress that we saw the other day and so forth. So we are subject to optical illusions, but these are more like hallucinations, really. Like the systems are very, very far from being correct. So what I would say, actually, I had on the previous slide, is hierarchies of feature detectors aren't wrong, but they're not sufficient either for building AI models, artificial intelligence models, or for understanding how the brain is. But it's kind of the only idea that people have out there. So the book, I have a couple over there for sale. Actually, I have more than a couple if you want. This new book, The Future of the Brain, is trying to look at where neuroscience is going. Like, in a way, I've been giving you a critique of where it's stuck. I think this is really quite a fabulous book. It's not an easy book. It's not airplane reading. It's written at the level that the Scientific American used to be, when the Scientific American was a little bit more challenging perhaps than it is today. But I think it's a pretty fabulous book. We talk about mapping the brain. I should say, first of all, that it's an edited book. So this isn't just my book. The subtitle is Essays by the World's Leading Neuroscientists. And I think we really do deliver what that title promises. So we have chapters on mapping the brain. So part of the question is like, how do you even figure out all the stuff that's in there? Where are all the neurons? How are they connected to one another? How do you figure out the basic landscape of the brain? Then we have chapters on understanding the computations that individual neurons are involved in. I'll talk about that a little bit later. We have chapters on simulating the brain, on how the brain understands language. We have a section on skeptics, so there's a lot of like excitement and hype in the media, but there's also reason for caution. I've actually cast myself as a skeptic. I'm in the skeptic section of the book, and also about implications. I don't quite have all of it here. Future of things like neurotechnology and prosthetics, which I'll take your questions about in a little bit. We have people in the book like Christoph Koch. Some of you might know his work on consciousness. He is the chief science officer at Paul Allen's Brain Institute in Seattle, which is the largest neuroscience institute in the world. They've spent a lot more money so far than the Obama Brain Initiative. So they're a huge neuroscience operation, and there's a chapter in the book about their project Mindscope, which is trying to figure out how the visual cortex of a mouse works. Which is, of course, not where we ultimately want to go. We ultimately want to know how our brains work, but it's a very good starting point. They have a very systematic plan for trying to understand that. Best chapter about that anywhere is in our book. This is George Church. He's trying to bring back woolly mammoths, and he was one of the people who basically launched the human genome sequencing revolution. His chapter is about using DNA as a way to figure out how the brain is interconnected, and as a way of recording what individual neurons are doing. It's called DNA ticker tape, and it's one of the most interesting ideas I've heard in years. So he's in there. This is Sean Hill. He's part of that European brain initiative. He runs the neuroinformatics at the €1 billion project. So we have really like the leaders in the field. This is Leah Krubitzer, who won a MacArthur Genius Award. She's got a chapter in there. These are two of our younger contributors, Misha Ahrens and Jeremy Freeman. Jeremy Freeman's my co-editor. They're both at the Howard Hughes Institute in Virginia. They've been working on these videos that I encourage you to see later about zebrafish looking at their entire brains all at once, which is amazing technology. And then, coolest of them all, we have Maybrit Moser, who, as some of you may know, won the Nobel Prize this year. In fact, the day before we went to press, so we got a little logo at the top, including this year's Nobel Prize winners, Maybrit and Edvard Moser. And part of what makes her so cool is that she, at her Nobel Prize, wore a dress, I think of her own design, with a picture of the grid cell neuron that she helped to discover. And she's got a chapter in there, the best in the world, about what it is that she actually won the Nobel Prize for. So the book is worth it for that alone, I think. My own view, and this comes from my own chapter and work with Adam Marblestone, who is at MIT, and Tom Dean, who's at Google, is that we need to rethink the metaphor of the brain being a computer. So a lot of people think that it's wrong, and part of the reason they think that it's wrong is because neuroscience has a very sorry history of explaining the brain in terms of the metaphors that just happen to be lying around at the minute at which people do the speculation. So Descartes, I don't know if I have more on the slide, thought that the mind was a hydraulic system, because when he was writing, like, the cool thing and the cool tech of his day was the thing in the French gardens that made, you know, water squirt in all kinds of different ways, and so that was what he thought was the right way to think about it. Freud was very impressed by the steam engine, and he has all these, you know, catharsis metaphors about pressure, your brain is under pressure, and so forth. So there's been a lot of history of, like, basically ridiculous metaphors. And of course, the tech of today is the cell phone, the computer, and so forth. And so when I might go around saying that the brain is in some ways like a computer, there's a kind of reflexive reaction to say, well, that's just the tech of the moment. And it's obvious that the brain isn't a computer of a certain sort, which is the kind of computer that I learned to program as not even as a teenager, as a preteen. I learned on the Commodore 64. And on the Commodore 64, you have a stored program. You go step by step through that program. That's how the program works. That's how the computer works. There's a stored program that does each thing one at a time. We talk about serial computers. The brain is parallel. The brain has 86 billion neurons working all at once. The Commodore 64 would load one instruction in memory, do one thing to one variable, then load the next instruction. It's sort of slow and painful, and you had to load it all off of a tape drive. And I won't bore you too much with the pain that I faced as a child learning how to program. But it was all step by step, and nobody thinks that the brain works that way. So we don't upload and download apps. You know, we don't have an app store for the brain. One thing you might ask me about is, will we ever get to the Matrix, where, you know, somebody can download into their brain the instructions for flying a helicopter, which would be very cool. And you can come back and ask me if it ever might happen. But for now, it certainly doesn't happen. That's not how our brains work. We don't download apps the way that computers work. And so people are like, okay, obviously the brain's not a computer. But I think all this shows us is that the brain is not a Commodore 64 or a Macintosh Plus. It hardly exhausts the notion of what a computer might be. It shows that an old version of a computer is not a good model of the brain, but that doesn't mean that there's nothing that we can learn from computers for how the brain works. So it turns out, first of all, that this idea of serialism, that you do each thing step by step, is really an artifact of older computers. It's not true of any modern computer. So any modern computer has many different systems that are working in parallel. So there is, for example, a graphics card that is putting up the display. There is an input card that is reading what's going on the keyboard. There's an Ethernet card that is communicating with the web. All of these things are working at the same time, just as you have many systems working in your brain. So it's kind of like a straw man to say the brain's not a computer when what you really mean is a serial computer, and that's not what computers are really doing anymore. In fact, understanding the brain as a computer has led to some real progress in neuroscience. So one of the most exciting applied things, and there's a lot of problems with it, I can talk about it, but one of the most exciting applications in neuroscience is this work by John Donahue at Brown University that you may have seen on like 60 Minutes, has been on television a lot. And he built a prosthetic interface so that the woman in the middle was able to control a robot arm such that she could actually take a drink. Right? This is a paralyzed woman, hadn't moved her limbs in years and years, and she's not actually moving her limbs here. What she's doing is, with her thoughts, moving a robot arm. I think this is a pretty amazing sign of what is to come in the future of the brain, is we're going to be able to interface with the brain. We're going to be able to read what it does. We're going to be able to read what it does and manipulate things. So what they're doing here is basically treating the brain as a computer. They're saying, what is the encoding scheme? How is information stored in the brain? Let's decode that, and once we decode it, we can use it to guide a robot arm. It's very literally taking the idea that there is a set of basically ones and zeros, or the equivalent, that we can decode and actually control things in the world. It's not perfect, but a lot of the imperfections aren't from thinking that the brain is a computer. They're from not having enough details about the circuit diagram to be able to read the information correctly. And then there's some other problems, like the risk of infection. So right now, in order to have a brain implant, you have to have something sticking out of your head. It's a constant risk of infection, and if there's infection, then you die. And so it's a very serious problem for now. It's a solvable problem, but right now, it's enough that, you know, most of you are not going to go home and get brain implants, even if, you know, we knew how to build brain implants that would enhance your memory and so forth. Probably not worth it for the risk of infection and having to go to the hospital once a week and so forth. But that doesn't take away from the fact that what is in your brain is basically information that is coded a lot like in a computer. So no, the brain is not a classical computer, but maybe it's something like a GPU. How many people here know what a GPU is? So GPU, graphics processing unit. This computer right here that I've borrowed has a graphics processing unit. Every like Sony PlayStation and Xbox has one. Pretty much all computers these days have them. What they do is they divide the labor so that the kind of decision making and things like that maybe happens in the main circuit board, the central processing unit, and then this GPU is a specialist that all it does is graphics. It renders the images, the three-dimensional images that you see, and it does that at the same time as the central processing unit. And it's a massively parallel device. So a GPU might have 1 billion transistors that are all going simultaneously. Well, that starts to look a lot more like the brain, where there's 86 billion neurons going simultaneously. Might be a better kind of computer model for what the brain is. I think an even better one, probably very few of you have heard of, is something called a field programmable gate array. A field programmable gate array, the field programmable part means that somebody can build one of these and then just before they use it, they can redesign what it's going to do. So most microprocessors, they're designed at the factory, they're fixed, they ship from the factory, they do one thing. But a field programmable gate array is not a specialist, but a generalist made up of a lot of little bits, each of which can be tailored to do particular things. So if you look under a magnifying glass, the whole thing looks alike. And that should make you think of this 6-layered cortex that's all uniform. But you can say, I'm going to have this part do arithmetic, this other part is going to do signal processing, this other part is going to do memory and so forth. I'm going to tailor it to my particular job. Car manufacturers, for example, use these a lot because if you're not going to build 1 billion of something, it's very expensive to set up a fabrication facility. It costs $100 million for each chip. You can make these things for millions of dollars. You save a lot of money dedicating it to a particular purpose. And what I'd like to suggest is maybe we need ideas like this in order to understand the brain. What's important about these things is you have this general substrate that you customize with different possible things. I would call them basic instructions. You have a, whoa, that was exciting. Big snowfall over there. We're okay, we'll be safe. In a field programmable gate array, you do everything in parallel, much like the brain, and by having a basic inventory of processes that you can recombine in different ways, you get enormous computational power, so essentially you can solve any problem you want. I think it might be a good model for how the brain works. As far as I can tell, nobody in neuroscience is really doing this, but we recently proposed this in Science, which is the leading journal in the field, I think in November, and so it's out there in the literature now. People are starting to think about it. Maybe I will skip this one for now. These building blocks might be things like topographic maps, which are kind of the ribbon cables of the brain. If you remember the old like 16 wires that would go from your printer to your computer, if you're my age, if you're a lot younger, you may have no idea what I'm talking about because they've all been replaced by USBs, but the older people in the room recognize those things. So they can be things like that. They're kind of like housekeeping basically for the brain, and then they might be these building blocks might be the kinds of things that cognitive psychologists talk about, like building blocks for working memory storage, building blocks for doing sequencing, for copying and pasting information across the brain in different ways. And there are several reasons why I think this is a plausible idea. One is that if the brain were like an FPGA, we could make sense of how it is that the brain, which has very slow individual neurons, is able to do so much in terms of the parallelism. So the FPGA circuit, the field programmable gate array, is a very good way of doing many computations in parallel. It's a way of doing things without a program at all. So instead of having a stored program that you load in and use at a particular time, you kind of unfold the entire thing so that it works at once. You customize it at runtime to do the kind of computation you need. And you could think, in a way, what you do over the course of your lifetime is you're customizing your brain circuitry for particular skills. You can learn new skills, and like playing guitar, as I did when I wrote the book Guitar Zero, or you can learn today something about neuroscience. Each bit is kind of customizing the set of circuitry that you've got. It also helps make sense of this idea of functional diversification, that different parts of the brain are doing different things. How are they doing it? The circuitry is all the same. We have no way to talk about that. But if what's really going on is that each area of the brain has a different complement of these special circuit types, that starts to give us a way of thinking about why there's specialization in the brain. It also might make sense with this idea of duplication and divergence, that the brain takes a basic theme. There's something called a central pattern generator that you find in many, many creatures, and maybe it diversified that, so there are different kinds of pattern generators in different places. That could give you some of the complexity that we might need. There's some possible evidence that points to how this might actually work. So we now know that gene expression varies in the brain. So the front of the brain and the back of the brain have different sets of genes. They're not very different, but they're different enough that they could be describing a code that would allow you to build the different building blocks of the brain in different places. We also know, now how many people know what synthetic biology is? So synthetic biology, you should definitely have a speaker mic on synthetic biology. Synthetic biology is going to totally change the world. It's the idea of reharnessing nature to build new kinds of things. So the evil part, I guess, is the GMO stuff that you think of from Monsanto, but there are going to be many, many applications. Like Craig Venter, who's one of the leaders in this, is trying to figure out how to build bacteria that will transform our sewage into energy and things like that. And there are a million possibilities. What people are trying to do in synthetic biology is to take the toolkit of nature and build new things out of it. And from that perspective, it looks like the toolkit of biology already has what we would need to build an FPGA, which is things like ways of having different sets of molecules specify different circuit types, different destinations for building things, and so forth. And there's also a very interesting set of molecular processes called alternative splicing, by which you can take one gene and build it in many different ways. And there are ways in which the biology seems to do that, for example, in different synapses. So two synapses can have the same genes, but instead of building the same proteins, they can build slightly different ones depending on the environment around them. So if you wanted to build an FPGA out of biological stuff, you could do it. So I think it's an idea that really needs to be explored. From the perspective of this audience, maybe the most fun in this book is the afterword that I wrote with Christoph Koch, who, as I mentioned, is the chief science officer at the Allen Brain Institute. I won't give everything away, but a lot of the book is nonfiction. People are writing about what we know right now, about what are the techniques that we're going to use in the next decade. And I remember in my talks, I'm talking about there's sort of the 10-year view, the 30-year view, and the 50-year view. A lot of the work in the book is really about the 10-year view. What do we know for sure is very likely to happen in the next decade. But in the afterward, Christoph Koch and I talked about where neuroscience would be in the year 2064 or 2065. So 50 years from now. We wrote it as kind of a science fiction piece. We imagined a visitor who we called Lem in honor of Stanislaw Lem, came from the future and is explaining to us what people discovered in neuroscience in the last 50 years. So we talk about things like nanobotic neural implants, which we think are pretty plausible, that you will have nanoscale robots that you can insert in your brain and do all kinds of things, like, for example, keep a backup copy of your brain, right? What happens if you're injured? Right now, if your brain is injured, we have no way of knowing how to restore your brain to the prior state. I was at the White House a couple of months ago, and there was an expert on traumatic brain injury there, and he talked about the state of that field right now, the pathetic state of the field that he's been working on for 20 years, which is right now, if your brain is injured, your loved one's brain is injured, all we can really say is the injury is mild, moderate, or severe. Like, we can't give any precision to how you're going to get better, whether you're going to get better. But imagine that you had brains that could, brain bots, little robots that could go into your brain, and record the state of all of the circuitry now, the connectome, the connections between all of your neurons, to give you a reference standard. And then those brain bots might also be able to manipulate the brain that's there. So if you were in some terrible injury, there would be a reference. We could say, this is what this person's brain is like before. We talk about that. We also talk about the limits. So it's one thing to restore a damaged brain by having its circuitry stored in a backup. It's another thing to fix a brain that was never right in the first place. So even if we could do that, that might not give us a cure, for example, for autism, where there isn't the sort of earlier version to revert to. We talk about things like that. We talk about whole brain simulations. We speculate that they probably won't come here. You all know Moore's law. Transistors keep getting cheaper and cheaper and smaller. That's going to run out. I mean, there's some argument in the field, but I think in general people agree that the transistors are going to stop getting smaller and smaller. We're going to reach a limit, and that's going to give us the limit on the speed at which computers can run. And that in turn is probably going to limit the we speculate, the ability to build a whole brain simulation that runs as fast as a human brain. Our best guess is that in 50 years we'll have brain simulations that run maybe 100 as fast as a human brain. So you'll be able to make a copy maybe of your brain, or at least like an animal's brain, and ask it questions, but it will be very slow indeed. And so we speculate about where all of these things might be. I'll say one more thing, and then I'll take any questions that you have about neuroscience, future of neuroscience, and so forth. I love questions. But at the end of the forward for the book, we say, if this book is a reader's guide to the future, it's not a foolproof crystal ball. I mean, nobody can speculate for sure where we're going to be 50 years. If anything, we see this book as more like a time capsule. Part of the fun is going to be for scientists and policymakers and so forth, the public, to come back to these essays a decade from now and see how we did. How close are the projections of all the world's leading neuroscientists? Did we get it right, or did we not? And a reviewer told us that they saw it that way, and we said we couldn't agree more. This book here is a time capsule of where neuroscience is right now, of how we're trying to push it forward, and we'll see if we're right. And I'd be glad to take any questions you have. Thanks very much.
I'm always going to start in the back because my last name is Taublev, and T was one of the last ones.
All right, I have 5, but I'm going to pick one. I have a sense of where you stand then on the singularity, but I don't want to make any assumptions, so I'd love to hear your thoughts on that. And given what you said about the brain and the limitations of computers, what your thoughts are, and as far as the tech community, and if as far as computers can develop is enough for them to implement the kinds of things we're talking about.
So are we going to be able to implement the singularity? I guess I don't quite understand the question.
Well, I'm wondering your position on the singularity based on what you've just talked about. And then it sounds to me like there's limitations that will not enable the singularity to occur, but I'm also wondering if the tech world will say, well, as far as we can develop is enough for us to create all these things we say we're going to create.
So in the interactive spirit that in some of my lectures, I will come back to you and say, what do you mean by the singularity? So actually a lot of people have different definitions of what they mean. So one definition is sort of, will computers become as smart as people? And another is like, are we going to merge with machines? So let me ask you first, which definition are you curious about?
I guess it's the replacement of a lot of human labor with computerization.
Well, that doesn't require a singularity. So I'll give you an example for that is the gentleman who drove me over here in an Uber, his job is in deep, deep trouble. So Uber is already investing in driverless cars. Google is investing in driverless cars. We don't need a singularity for that. So a singularity might be defined in terms of computers being as smart as us, but there are a lot of individual problems that depend on, or they can be solved by very careful engineering to that problem. So Google's driverless cars are very narrow systems. They don't understand the world. They don't even really understand driving. They've just memorized a lot of circumstances. That makes them ill-equipped to ride in the rain. I would not get in one in the snow or in Manhattan or Brooklyn probably. But eventually you can just memorize enough things and solve the problem without being that smart. That is going to have a huge impact on the labor market. All the drivers are in trouble, taxi drivers, Federal Express drivers, and so forth. So whole markets are going to disappear to automation in the next 20, 30 years. Fast food workers, not everything will disappear. Entertainers are safe for a while. People will always be interested in seeing human beings do certain things, just like we still like horse-drawn carriages in Central Park. There'll always be a little bit of room for that. But I think we have a serious employment problem in front of us, even if we don't reach the singularity. Now, if we do reach the singularity defined as machines are basically generally as flexible and smart as people, then we have an even bigger labor problem. And I think in the long run, that is where we're going, and it's just a question of time. So a lot of people think AI is 20 years from now, like strong AI. I think that's absurd. If you look day to day at where the work is, we're just not 20 years away. We might be 50 years away. I sometimes show, when I talk about AI, a graph of artificial intelligence predictions, and people keep predicting that AI is 20 years away, but they've been doing that since 1950. So Kurzweil does it now, and other people did it in the 50s. I'm not sure those predictions are right, but it's not 100 years away, and it's certainly not 200 years away. So eventually, in that sense, the singularity part of machines being as smart as people, that is going to come. It's just a question of time and engineering and how much investment people want to make. We need some more good ideas, but it will happen. Then there's a part of the singularity which is about like human brains merging with machine brains, and I think that's probably going to come too. I mean, the stuff I showed you with the the robot prosthetics, that's already a step in that direction. There are technical problems that need to be overcome, like the infection problem, and how do you do these things in a permanent way? So every time the wires jiggle around, you've got a problem, and every time your head moves around, you've got a problem. And so we're a ways from being able to do that well enough, but one of the chapters in the book is about a way of using ultrasound with something called neural dust that might be implanted. So there are ways of approaching these things, and I think over the next 5 decades, there'll be a lot of progress in many of those areas.
Okay, next.
Thank you very much. Really appreciate everything.
Here, we got a mic for you.
I have 2 questions for you. I heard a lot of inconsistencies on precision in neuroscience from your perspective. And I was curious to understand, what is the problem with petabytes or zettabytes of data and pattern recognition, instead of trying to get down to the precision of trying to find that specific neuron that actually connects it all together? That was the first question, because I see a lot of amazing work happening, and I think that when quantum computing gets to a certain spot in the next couple of years, that leapfrog of 5 or 10 years of AI.
Let's stick to the first question, because there's already several things I want to respond to.
First question.
One is that it's not clear what the impact of quantum computation is. We talk about that as well a little bit in the book. So far, quantum computation doesn't really do anything that you can't do with classical computation. I mean, there's why can't I think of the deep wave? That's not the right name. D-wave, sorry. The D-wave machine, in comparisons people have made, it doesn't do anything. The classical machine can't do. It doesn't do it any more cheaply and so forth. So it's not clear what the impact of quantum computation is. But the real problem with the exabytes, I mean, I think we need the exabytes of data, but it's a needle in a haystack problem. So we don't know how to search that data for the right kinds of things. We don't even really know what we're looking for. So we don't have sharp enough hypotheses about what to test. It'd be like if I said, here's all the data from all the people on the planet Earth. I want you to, and I'm not going to tell you anything, but I want you to find how people are celebrating their birthdays tonight, without any prior notice. Like, you need something to go on, and we don't know what that something is. So it's not a problem of lack of data. It's not even necessarily a problem of lack of computational resources. It's really at the moment a lack of ideas. That science in general proceeds by people testing hypotheses. I tried to give you one tonight that's pretty vague, to be honest and fair. We don't have, precision is a word that you used, we don't have precise hypotheses yet to test. And if you don't have precise hypotheses and you have an exabyte, you have a problem. And it'll be solved eventually, but we're not there yet. We don't know how to approach it yet. And I'll only take one question per person, probably, because there's a lot of hands. Mike's doing them. Mike is doing the mic.
Does your survey of brain research make you optimistic or pessimistic about the utility of cryonics?
Pessimistic. So the question was about cryonics, and I guess you're talking about like preserving brains, and people also talk about uploads.
Even though we don't know exactly how the brain works, from what we do know, we'll let you solve later.
I mean, I guess I could ask you, what time scale you're talking about. So I don't have any hope for cryonics doing me any good. I'm in my 40s. We don't have to get too specific. And so, if I'm really, really lucky, I'll live another 50 years. And I don't think in 50 years that we will be able to get quite enough detail to make significant reconstructions, aside from the fact, and I guess there are different things that you could talk about. So like uploads is something that people ask about. Could you build a computer simulation of my brain or your brain, things like that? I think we're pretty far away from doing that. In terms of just like keeping a brain booted and taking it from one person's skull and putting it in another, maybe that's a more plausible thing. But in terms of like reconstructing a brain from scratch, building a simulation of it, that kind of thing, I think we're a ways. I guess I could ask you what you mean by cryonics.
Would it be worthwhile for someone in your age group to have the brain frozen using today's freezing technology, and within that span, maybe we wouldn't know what to do with it, but then in the next 50,
yeah, I mean, it's possible. I mean, I'm not rushing to have my brain frozen. I mean, some of the reasons are really more like business reasons, like are the places that are going to keep your brain alive, are they going to be alive in 40 years? And so, the kind of control of possession. I think in the very long term, but we don't know how long a term it is, those kinds of techniques may actually have some impact. Might also be that, it's almost irrelevant because it takes 1,000 years and, you don't really want to be around because things are going to be so different and you're going to be so far behind. Like, there's a lot of imponderables. In the short term, we have no idea what to do with a frozen brain. Sorry to say.
If you have any core questions that you could solve, kind of pick one. What would it be, like long-term memory? How does that work? You brought up some of these.
For me, it would be what a computer scientist would call variable binding. If I could solve one problem, how does the brain do X? It would be, how does the brain take a value from a computation, store it temporarily, and then run a function on it? So if anybody's programmed in Lisp or Python or most computer programming languages, the essence of those languages is you define functions. You can run those functions on a whole range of different inputs and get some reliable thing. You can think of them as subroutines, if you know that word. The brain needs to be able to do something like that, and we don't know how it does. Once you understood how the brain does that, there'd be a whole bunch of things that would open up. Like, if we could understand how the brain does variable binding, and performs operations over variables, we can think also of like algebraic variables, then we might be able to unravel how we do language, which would be something I'd really like to understand. Until we get to that point, it's like too large a bridge to jump. So it'd be like trying to understand how a computer works by just knowing about electricity without knowing about transistors and microprocessors. You need to like bridge some steps, and I think the key bridge to understanding human cognition and probably a lot of animal cognition is this variable binding stuff. So if there's one thing I could solve before they froze my brain, that would be it.
Hey, I sort of don't know how to phrase this into a question really. I'm just curious your thoughts on it. Because you said you do a lot of work with speech and language. I always kind of considered humans above many animals in just the way that we have language. We can communicate with spoken word. But you can take whales, finbacks, and whales, for instance, have really complex ways of talking to each other.
We don't know that much about them. I mean, I wouldn't. There's certainly some complexity there. We don't know that much. I always think about the Far Side cartoon where they're writing down. I think it's dolphins rather than whales, but they're writing down. A couple of scientists are writing it on the blackboard, and they say, "We got another one of those, say, habla españols." I don't know what these guys are talking about. And the point of the cartoon is the whales could be saying lots of interesting stuff, and we don't know how to decode it. There are some ways you can do kind of information theoretic decryption and stuff like that, and get some sense. We don't really know. I think we're fairly confident that chimpanzees aren't saying very much. We don't really know that much about what the whales are talking about. I think in general, language does set us apart from other species, mostly because it's a really efficient way of transmitting culture. So if you took any one of us without training, when we were born, put us on a desert island, we would not know how to reconstruct cell phones or build cars or any of that stuff. And the fact that we can transmit all this information really boils down in part, or boils down too strong, but stems in part from language and the way that we can really efficiently communicate information with that. And I think that is a central part of why we have a very different niche in the world. Pinker calls it the cognitive niche than most other creatures. Two or three more questions? I have two little kids, so I can't stay out all night, sadly.
Understandably. And then after that,
and then I'll sign some
more
books if anybody's
sign
interested.
And sell. Please support our authors.
Hi. I don't know if this is a question, but it's a thought. Would it be too speculative to say that some of these things that neuroscience can't answer partly has to do with something even more big that we don't understand, which is consciousness?
I think consciousness is even worse. I'd reverse your thought. I'd say the chance that we'll understand consciousness before we understand the rest of the brain is negligible. That consciousness is a special thing that the brain does. There are a lot of less special things that the brain does that are probably easier to understand, that we have a handle at least what the question is, and we sort of know what an answer would look like if we found it. We might recognize that answer. These are on sale for $20 each, discount price, over there in a second. So we don't quite know what the answer would look like. For something like short-term memory, at least if we had the right explanation, we'd know that we had it. And with consciousness, we're not quite sure what that would look like. So I think it's a harder challenge. People don't quite know what they're looking for. My colleague at NYU, David Chalmers, has talked about the easy problem of consciousness versus the hard problem. The easy part is like, how do we know which information is active in our brains at the moment? That we've got a handle on. People are making progress there. So there are things like attention. What are you paying attention to? All these things happening in the room, but most of it, like the background noise, gets filtered out. What makes it so that you can kind of contemplate it? That we have a handle on. We're getting there. And then there's this part, like, what is it to be able to reflect on your own thoughts, for example? We just don't really even know how to ask the question.
Okay.
Two more?
Two more. Okay.
I was just wondering if there's anyone, like when you talk about it, it keeps on being brain. But I mean, I know the brain is central to much of the processing, but at the same time, we are a whole system. Like there's a lot of nerves, not that many, but still a number of nerves that are outside of the brain that are still part of this larger network that is really one single unit of our neural system. Is there anybody who's sort of addressing some of the work that ends up being done by these extremity sections?
There's actually a great book called The Second Brain, I think, by someone, I think his name is Gershon, or very similar to that, which is about the stomach, which is actually part of the nervous system and does a lot of interesting stuff. So there's certainly work on that. I actually have a note in my very long to-do list, which is make talk less corticocentric or cortico-chauvinist. I realize that I'm a chauvinist and I'm mostly talking about the cortex. There's a lot of other stuff going on, even just inside your skull, and the spinal cord can do a lot of pretty interesting things. There's bits and pieces of work on those kinds of things. I am in fact a chauvinist. I really care ultimately about human cognition, like how it is that we can have a conversation like this and I can transmit information and you can learn things. But it's pretty interesting that the spinal cord can like keep your balance as well as it can. I ride a unicycle. A lot of that is somehow probably in my spinal cord, and that's from the perspective of cognition kind of interesting. And then the stomach is doing a bunch of information processing and giving you
the eyes, I mean, like
the eyes are actually, the retina is actually very well understood compared to the rest of the brain. Someone who wrote a great book, or had a book with a great title, I won't say it's a great book, called The Retina, an approachable part of the brain. The book's outdated now, but we know there are about 50 kinds of neurons in the retina, and we actually have a good handle on what they are. People are starting to figure out things like, how does the retina figure out whether something's in motion or not? And people have been arguing about this for 40 years. They haven't quite nailed it, but like we're a lot closer to being able to nail that kind of question. So the retina is actually something reasonably well understood. There's now FDA-approved prosthetic retina because we know kind of what information processing it does. The retina is a computer. It's basically like a CCD sensor that's taking in light, recoding it. We now know enough about that recoding that we can replace it.
Okay, and then speaking of nailing the last question.
That was going to be my choice since he came up and talked to me earlier, and I like a friendly person.
This is just a kind of basic question. What percentage of the brain does the average person use daily? In the movie Lucy, they had it at 8%. But I've learned over the last 10 years that numbers changed to 30, 40, 50%. Different scientists are giving different numbers.
It's a made-up number, and Hollywood certainly had fun with it. Most neuroscientists would say it's wrong, but I don't think it's as wrong as they'll say. So here's a way in which it's totally wrong, which is it's not like you have some gray matter sitting there that is just unemployed, never does anything, right? I mean, that it doesn't work that way. Like, nature basically doesn't keep brain tissue around without a good reason. It's very expensive. It's very metabolically costly. And so creatures have brains that kind of suit their niche. I mean, it's maybe not perfect, but roughly speaking, most of the brain does get used. The way in which it's a little bit right is that the brain has this really cool switching property, that it switches in just the right thing at the right moment. Nobody has any idea how it does it, but in any given moment, you might actually be using 8%. Then you use a different 8% as you walk across the room, and in the course of a day, you might use most of it. That doesn't mean there's no room for growth and things like that. My book, Guitar Zero, is about how, even if you're 40, you can still learn to play guitar. There's lots of capacity that can be pushed further than it is, I'd say. But all of the brain gets used fairly regularly as far as we can tell. But at the same time, the brain is really good about saying, right now, the set of troops I need to solve this problem are these. Maybe you can think of it like an orchestra. You don't want 100% of the instruments to be playing at any one moment. Maybe in the big finale they all play. But there are lots of passages where you want just the right set of musicians to be playing. Somehow the brain accomplishes that brilliantly. And whereas an orchestra is doing that with some kind of score that's been written out in advance, nothing's written in advance. You're always reacting on the fly dynamically. And the brain sorts out, this is a part of the orchestra that needs to play right now. And that might actually be like 80% of the brain's instruments, so to speak, are playing at any given moment. All right, thank you very much. I'd be happy to sign books, and I'm glad to come back.
And definitely urge you to patronize Gary and his books. And if you'd like to stick around and maybe just go into circles or even assemble by the beer and wine, I've got some discussion items.